Hello and welcome to a new video here in the video series of myself looking at websites of quantum companies, which is quantum computing, quantum communication and quantum sensing. As always, before we start into the new episode, make sure to get yourself something to drink because we always want to stay hydrated. And then let's get right into it. So today we are looking into QuEra. So it's this website here, QuEra, with this bracket notation around it. And we see the best way to quantum, it says at the very beginning. So it says neutral atoms are considered by many to be the best approach to achieve large-scale fault-tolerant quantum computers. QuEra is the scientific and commercial leader in neutral atoms. So what do we know from that? What do we learn from that? Well, that basically means QuEra is probably another one of those companies that supply hardware for quantum computation, but it's a different approach than what we saw before. So remember, we already had superconducting qubits. We have been, I think, talking about ion traps. There were the what was it called? I don't remember the name of it right now. I think it's cat qubits. Hopefully I'm not confusing that now. And now we look at neutral atoms. So neutral atoms is probably something similar by the name already to ions, because ions, they're also atoms, but ions, they are ionized. That means they have an electric charge, a net charge. So that means there is one electron missing in the atom. And here we now see neutral atoms. To talk about how this actually works is a whole nother session in itself. I'm not sure how much we will learn about it here on the website, because confining an ion, you can basically just use an electromagnetic field. But then for neutral atoms, actually it works similar, but also it works different. Let's see how what we can learn here on the website. We already see here, explore our roadmap. So as a proper quantum computing company, of course, also QuEra has a roadmap on how they want to scale those systems, but we are not looking into this right yet, because first of all, let's see what else they are telling us here on their website. So it says trusted by, and then we see a couple of labels. So there was the Open Quantum Institute before. We see NVIDIA here, that's Wolfram Alpha, all the physicists know from solving integration problems. At least before there was OpenAI. I don't know if nowadays people use something else. And some other companies, I mean, not small labels, I would say. Okay. Then we see here the analog 256 qubit quantum computer. So that's the system as it appears to be, like a rack, I guess. It looks like a rack. It has the shape of a rack, but you can already see here the door is opened a little bit, and inside you see something that looks like an optics lab. So, I mean, you see the optical table maybe a little bit here, and then there are some wires going up. And it's also completely black, so it's protected from light around. So that already might indicate that something is happening here with optics. And then it says interested in Gemini, our 256 qubit gate model computer, qubit gate model computer, contact us. So basically you can either reach out and buy the computer, or you can access it on Amazon Braket, which is the quantum service, the quantum cloud service from Amazon. Then it says experience the power of neutral atom computers, analog or digital quantum computation, the best way to quantum machine learning, optimization and simulation. Join us in the exciting era of quantum error correction. So what do we take from that? So there is 256 qubits. That's quite a lot already, right? We've seen machines with much less, like 8 qubits, which you could buy for, let's say, educational projects. Here we are looking at 256. That's already quite a bit. Then it says something about analog and digital quantum computation. That's also an interesting topic to go into, probably in an additional session. And then it basically says something about quantum error correction, which we've also been discussing before. It is the concept that now we are in the NISQ area, where qubits make errors because of the reason that They always can interact in some way with the environment. There can be errors in the operation of the qubits, and those, because everything is entangled, they can really accumulate across the whole system and spread across the whole system. So the error correction in itself is a whole discipline, and this quantum error correction, we think, might be needed to get those systems in order to finally, at a final stage, operate proper quantum algorithms. Okay, then it says again, explore the roadmap, which we will definitely do. And then what do we have here? Design and test with Blockade, which is a trademark, our open source software development kit. So they also have a software which they developed themselves, apparently, which is called Blockade, with Q, of course. Let's see what it does. It says powerful and flexible, exceptionally efficient from design to neutral atom quantum execution. So, and here we see what it looks like. Looks to me quite Pythonic. So basically that looks very much like it creates a graph. Plotting the results of Rydberg density. So Rydberg atoms is what is behind this whole neutral atom thing. So what I would guess is it can, native encoding of neutral atom quantum features such as Rydberg blockade, Hilbert spaces, flexible geometries, and continuous time control, supports GPU acceleration. So either it is to basically couple a GPU with the quantum computer, or it might be to simulate or emulate the quantum computer. That's not completely sure right away for me. But it says deployable in high-performance compute environments, and it's written in Julia for maximum performance. Julia is like a Pythonic way of performing high compute, like in the efficiency similar to a C environment. And then the best way to develop, deploy, and execute code on Amazon Braket, so that you can really, so it looks like you can really go all the way to execution with this in the cloud service. And then there is updates down here, which is fairly up to date. This is being recorded end of May, and we see here some news end of May. So that looks very up to date. And here it says work with us. So there is some ways, I guess, to get started. Premium cloud access on-premise, so you can buy a system, you can buy time on a system, algorithm co-design, so they probably also help you to implement algorithms on their system, quantum machine learning, quantum optimization, and simulation. Okay. So that was the first side. There is something about neutral atoms. I will only very briefly go across it because I think it's worth a whole another video in itself. It's a very fascinating concept, that I can tell you. But that looks like the chip which is actually being used. Here it says something about the advantage of neutral atoms, nature's perfect qubits. Again, like we are talking about atoms, very similar to what we learned from the ions before. They're all the same. So you don't need to do fine-tuning for the specific chip because there's no imperfection. They're all exactly the same. That's what I guess they refer to when they say nature's perfect qubits. Error resiliency, high-quality multi-qubit gates because you can better also entangle them. Small footprint, I guess because they can quench it down to this, what looks to me like a chip. Field programmable gate arrays, so field programmable qubit arrays. Sorry, that was my bad. That was a bit on the wrong track. So FPQAs, also trademark, very nice. Highly scalable modular architecture, hybrid operation modes, and then post-classical compute power. Very nice, very good subscription. And then there are some more details here. So that's going to be the explanation of what this whole thing looks like and works like. I will not go into the details. I will make a separate video about that. But basically, you see there is an atom, there are two states, there is an electron, and then you can use lasers to control and measure those states and perform operations. And this is very nicely explained, like what a single qubit looks like, what multiple qubits look like, and how to entangle them. Then it also explains the footprint part of it, the flexible configurations, qubit shuttling, that's also very cool. Then we have digital and analog quantum operations. That one I also need to understand a little bit better for myself. Okay, then we have quantum error correction. There is some archive paper, so it looks like they also do research on this and they publish it. That's very nice. Archive is an open access way to publish stuff, so probably very worth to check it out. There's also some Nature and APS publications. Very nice. Let's look at the roadmap. So that's going to be an exciting one. That one has been promoted so much on the website, there needs to be something exciting to that as well. Okay, a unique hybrid approach, delivering value and utility at each step. So what do we have here? Step 1 is the 256. So that's already a strong step if that's the first step, right? Solving hard problems at the edge of computation with 256 entangled qubits and field programmable quantum arrays, FPQAs. Then we have the early quantum error correction. So logical qubits, case-based operations, native multi-qubit gates, long coherence times, okay. And then it goes on to say large-scale fault tolerance, so efficient error correction, scalable control, small footprint, so it says 10,000 atoms in a millimeter squared, and then quantum advantage. So we see that like in step 3, they want to reach this quantum advantage. Now the difference being, if I compare this roadmap to other roadmaps, this is very much on the conceptual level. We don't have any, let's say, time steps on that yet. I'm not going to say if I find it good or bad, to be politically neutral here. Okay, and then what? Here we see some. We actually see some timestamps here, but that's from the past, so 2017 to 2025, building on a series of scientific breakthroughs. So that's probably the most important breakthroughs in this area that have been achieved, and that led to this basically start of QuEra. Then it says enabling new applications. So here we go into the applications again. We see Hamiltonian simulation that looks very much like a molecule. So I guess that's also again heading towards material science, pharmaceuticals, discovering new molecules. Then we have optimization. So this is the logistics, the good old traveling salesman problem. And we have machine learning, quantum machine learning, which is something that excites a lot of people right now. Okay, so with that, let's take a look into the products that QuEra is offering. We see analog quantum computer, on-premise computers, premium cloud access, algorithm co-design, and blockade emulators. So let's start with the first one very briefly. So here we have the 256 qubit analog quantum computer. That's the one that we saw before already. Here it says something about how to get started on such a machine, so you can learn something about it. There is also access via Amazon Bracket. Okay. And what else do we have? Available windows. Okay, so they have a system on Amazon Bracket, and here you can probably, already like in a way schedule time, I'd assume. Calendar shown in, okay. So there is some way to access the system, and sometimes it might be blocked. Okay. Then we have typical specifications. Here we see some Hamiltonian. Okay. Analog mode operation covers a wide family of Hamiltonians within the following format. Okay, so that's kind of helping you to figure out whether the problem that you're trying to solve actually maps on the architecture. There's some information here also on the system values. Okay, and then we have best practices down here. Let's check out if we find something new here. Seamless integration with existing HPC resources. So really the idea is to basically add your classical high performance compute resources with the on-premise quantum computer. So to put your quantum computer right next to your supercomputer. So this is targeting Of course, the big, let's say, compute providers, but this is also targeting large organizations that try to build an on-premise quantum solutions, as well as research institutions which are looking into this. And I think research is right now also a pretty big customer here. Okay, there's some information on that. Then we see the premium cloud access, which I think I don't need to go through the details here. I mean, you know what the cloud is. You have been probably using it already. Here are some of the benefits, which says you can get an exclusive access. That I think is important, because if you really want to run business application on it, you want to make sure that the machine is really blocked for you. You even get support from a scientific team, which I think is quite helpful right now, because it's not so easy to actually get your stuff up and running on those systems, especially if you've never been working with those systems before. Early access to advanced features, business service level agreement. You also get instructional training, which is again important to get a training on how to actually use it, regular office hours to get support when you have questions, consulting options, so you can even get probably a consultant from QuEra to help figure out where there are actually problems in your business that might become relevant in the context of quantum, and then fixed cost, fixed term contracts. So, okay. There's algorithm co-design, which I guess, is basically the explanation of how you design together with them, and the blockade emulator, which is this software development kit that we saw before. Okay. Very good. Then we have the solutions part. Here they actually do something very interesting. They split it between the industries and the applications. So in terms of industries, we find the usual suspects. We find finance, chemical and pharma, which I also call material science into. There's logistics, automotive, the energy grid, and I also see the public sector, which I haven't seen before. So let's click on that. What does it say? Okay, economic growth, for, workforce development, and creating a vibrant hub. Okay. So that's for local economies. Okay. Interesting. Let's see if there... no, that's something that we've seen already. Okay. So this is probably... that's probably what this is about. So creating like an economy around quantum, creating the workforce, and then, attracting both industry and academia. Quantum technologies create a national or regional magnet for high value activity. Okay, got it. And then we have the applications, which also in a way are our usual suspects. So we have optimizations problems, which is, for example, prevalent in finance and logistics. We have the machine learning, the quantum machine learning. Simulation is like simulating the nature, the quantum nature, so molecules and so on. We have the HPC, so the high performance centers, and national programs. And then there is also the news and insights tick, which shows the events and latest news. There's also a podcast, which I think is a very good idea to also have your own podcast, or have be present in people's podcasts, because it is important to also get your messages out, to get people the chance to actually learn about your product. So I really like that idea. And then there is this section here about the company, which probably tells a little bit about how, the core values, more science, less fiction, high quality, no shortcuts, learn together. Then there is something about the team, very nice. So you can see who's actually working there and who are the founders. So that all looks very good to me. Then there's career partners and some media kit. So with that, I think we are already at the end of this video. As always, very important, stay hydrated. And then I will see you in the next one. Bye bye.